My name is Jessica Webster and this is my Lab 7 Black Hole Video Report. In this lab I observed a star with known mass orbiting a stationary black hole with an unknown mass through a Python simulation. Through this lab I also saw how FNet and the changing momentum's vector components correlated. The result of my lab was that the black hole had a mass of 1.98 times 10 to the 31st power. Also, FNet's parallel component equals the change in momentum's parallel component, and FNet's perpendicular component equals the change in momentum's perpendicular component. In this lab, we observed the star curving around the unknown mass. We knew there was some force acting from the mass's position because if nothing was acting on the star, then it would continue to move at a constant velocity in a straight line. I broke the FNet vectors down into its parallel and perpendicular components to help visualize what was going on. The FNet vector, in red, is in the direction of the mass towards the kissing circle, or the circle tangent to the star's path. FNet parallel, in black, changes the FNet vector's magnitude, and FNet perpendicular, in blue, changes the FNet vector's direction. The simulation correctly found the mass of the black hole using Newton's gravitational force. Newton's gravitational force is the universal gravitational constant g, which equals 6.67 e to the negative 11 times the masses of the star and black hole divided by the distance between the moving star and the stationary object. I was able to break my vectors down into components using the momentum principle, the change in momentum equaling FNet, knowing that FNet equals both my parallel and perpendicular components. To initialize my simulation, the star mass equals 1.989 e to the 30th power kilograms. Delta T equals 86400 seconds, which is 1 day, and the star's changing position is loaded from a CSV file with the appropriate data. Also, the black hole position vector is 2e10, negative 3e10, 0. I edited my Python code to correctly calculate momentum using P equals mv. After finding the change in momentum, I equated this to FNet, which I use in my gravitational force equation to find the black hole's mass. For visual purposes, I separated FNet into parallel and perpendicular components. The program mimics the actual data pretty well since the black hole's gravitational force on the star is the only substantial force acting on it in space. If you recall, our version of the momentum principle states the change in momentum equals FNet, but really FNet causes the change in momentum. So FNet is the cause and the change in momentum is the effect. Also, as you can see from my code, FNet has the same value as the change in momentum, and FNet's parallel component equals the change in momentum's parallel component, just as FNet's perpendicular component equals the change in momentum's perpendicular component. But it's important to remember two of their main differences. One, FNet and the change in momentum measure different things. FNet is the total surrounding forces acting on the system, and the change in momentum is the change in momentum over a time interval. 2. The change in momentum is an approximation since FNet is really equivalent to the change in momentum instantaneously. However, as t approaches 0, their equivalence becomes more realistic. If our black hole is interchanged with a different black hole at the same location and there are no changes to our star's motion, we cannot tell the difference. There being no difference in our star's motion implies the black hole's mass is also unchanged. Thank you, and I hope you enjoyed my lab.